All right, welcome to the gases unit of Chemistry 20. There will be a little bit of theory in this unit, which we're going to start off with here, but this unit leans more towards calculations. So we're going to be eventually getting into calculations using Boyle's law, Charles' law, combined gas law, ideal gas law, and law of combining volumes. We're also going to do some conversions with pressure and temperature and volume as well. Okay, so starting off with some properties of gases that you need to be aware of. There's 5 properties that we're going to be going over. Okay, so the first one's going to be that gases always fill their container. So whatever size container you put whatever gas into, it's going to expand to fill whatever container you put it into. Okay. Now the second property of gases is that they are highly compressible. Okay. So what that means is if you initially put a gas into a larger container, you can decrease the size of that container to kind of squish the gas molecules together. And the reason why we can do this is because gases are made up of mostly empty space. That's why you can compress them. So let's just write that as a little note here. So because gases are mostly empty space. Now the third property of gases is that they diffuse uniformly to form a homogeneous mixture. Okay, so diffusion is just when some substance goes from a high concentration to a low concentration. Okay, and it's kind of like a passive form of creating a homogeneous mixture. Passive just meaning you don't need to put any energy into it. Okay, so if we look at this diagram here, initially we have this ideal gas here in a high concentration. Okay, so I'm just abbreviating concentration to CONC. And then over here where there's the vacuum, we can say that that's a low concentration of whatever gas we're talking about. Okay, now if we turn this valve here so that we can have the gas move from a high concentration to a low concentration, eventually in both like sections of this container, we get a relatively even mix or even distribution of gas molecules, and that's just what they're meaning with homogeneous mixture. It means like there's the same concentration throughout whatever area you're talking about. Okay, but the main idea here is that like gas particles will move or they'll diffuse from an area of high concentration to low concentration until the gas particles are evenly distributed. So let's write that out. So gas particles will diffuse from an area of high concentration to low concentration until the gas particles are evenly distributed. Okay. Another property of gases here is that when you heat them up, they're going to expand. Conversely, when you cool them down, the gas will contract. So if you, in this diagram here, they're taking a balloon and they're heating it up, which is causing the gas molecules to expand, okay, or move farther apart from each other. However, if we took this same balloon here, then what would happen is if we cooled it, that balloon would shrink in size. So let's just add that in here. Okay, so when gases are heated, they expand. When you cool them, they contract. Okay. And the last property here is confined gases experience increased pressure when heated. Okay. So to summarize that up in shorthand, if you increase the temperature, so I'm abbreviating temperature to T, then the pressure is going to increase. So I'm abbreviating pressure to P. If we decrease temperature, then we are going to decrease pressure. Now, the reason why that happens is because pressure is created by gas particles hitting the sides of a container. So if you increase the temperature of gas particles, they're going to be moving faster. And that means they're going to be hitting the sides of the container faster. So, as I said, gas pressure is created by gas particles hitting the sides of the container. If they hit the sides of the container with more frequency, that's what increases the pressure. Okay, so let's write out what I've just said about how gas pressure is created. So gas pressure is created by gas particles hitting the sides of the container. The container being whatever container that your gas is in. So increasing the temperature, which I'm going to abbreviate to just temp, increases the kinetic energy for gas particles. So kinetic energy is just the energy of movement. So if your gas particles are moving around faster because you heated them up, then they have more kinetic energy. So increasing temperature increases the kinetic energy of gas particles. Therefore, gas particles move faster and hit the sides of the container faster, therefore increased pressure. Okay, so those are the 5 properties of gases there. And all of these properties can be explained by something called the kinetic molecular theory. So what the kinetic molecular theory is just these 3 points below here. Okay, and I've talked about some of them already here. So statement number 1 just says the volume of gas, most of the volume of a gas is empty space, which we talked about in property number 2 there, where gases are highly compressible. With statement number 2 there, gas molecules are in constant random motion. Okay, the only time they wouldn't be in motion is if they were at absolute 0, and absolute 0 just means you're at 0 degrees or 0 Kelvin, which is negative 273.15 degrees Celsius, which is a pretty hard temperature to reach. So that's why we can say that gas molecules are in constant random motion, and the molecules travel in straight lines until they collide with gas particles or walls of a container. Okay, so the walls of the container bit, that has to relate to how gas pressure is created there, so which we talked about in the last point, or the last property there. Okay, now the gas molecules interact with one another and with the walls on a container only through elastic collisions. So what elastic collisions means is that when you have 2 gas particles collide, so if I drew a picture, let's say that's a gas particle, that's another gas particle, and let's say they are moving towards each other and they collide, okay, what they'll do is they'll just bounce back off of each other, okay, and no kinetic energy is going to be lost, or in other words, kinetic energy is conserved. That's just 2 ways of saying the exact same thing. Now, another way to say like that kinetic energy is being conserved is when these 2 particles hit each other and then bounce off of each other, like they're not going to slow down. No energy due to motion is going to be lost when they run into each other, or when they run into the side of whatever container that the gas molecules are in. Okay. Now, when we're doing calculations, oftentimes we are going to assume that we are working with ideal gases rather than real gases. The reason for this is just to make doing calculations a lot easier. And there's some assumptions that go with assuming that we're working with ideal gases. Okay, so our assumptions are that gas molecules are very far apart in an ideal gas, and compared to the size of the distance between molecules, we're going to assume that the gas molecule size is negligible. However, in real life, at high pressures, the molecules are forced a lot closer together. So if you want to see an example of that, right? If we compress the gas, all of these particles are a lot closer together, and so they're bumping into the sides of the container a lot more, and that's what creates that higher pressure. Okay. So at high pressure, the molecules are forced much closer together, and their size does become significant in a real gas. So in other words, the empty space available is less than the size of the container. For an ideal gas here, the gas molecules are in constant random straight line motion because no forces exist between them. So that's for an ideal gas. However, in the real world, as the temperature decreases, molecules are going to slow down. Okay? And at some point, the intermolecular attractions, so that could be London forces, dipole-dipole, or hydrogen bonding, they may cause the molecules to stick together and the gas becomes a liquid. for an ideal gas, we can assume that they undergo perfectly elastic collisions and there's no energy, no kinetic energy lost. But in the real world, molecules of a real gas are more like soft spheres, and when they collide, they lose a little bit of kinetic energy. Okay? And what that means is that the pressure of the gas is actually going to be lower than what you would expect when you assume you have an ideal gas. Okay. So we've been talking about kinetic energy, which is just the energy of motion, and that's closely related to temperature because temperature is just a measurement of the average kinetic energy of particles in whatever substance that you're talking about. Okay, so the more your particles are moving, the higher the amount of kinetic energy they have, and therefore the higher the temperature they have. Now, moving on to pressure. Typically, we are going to work with pressure in kilopascals. That's not to say that's the only unit of pressure that we're going to work with, but kilopascals is the most common one that we're going to work with just because that is like the standard unit for pressure. Okay, and now pressure typically gets measured with an instrument called a barometer. Okay. Now, you will need to know how to convert between pressure units because, like I said, even though kilopascals is the most common one, that's not the only unit of measurement for pressure. Okay, so we have this conversion line, which is pretty important here, so let's highlight it. And now what this conversion line is saying is that if you have 760, so this means millimeters of mercury. Okay, so sometimes when you're using instruments there, such as a barometer, it's going to measure how much pressure the gas, or typically the atmospheric gases, are applying on the mercury in the barometer. And so that's why we have 760 millimeters of mercury. That is a unit of measurement for pressure. So 760 millimeters of mercury is equal to 760 torr, which is equal to 101.325 kilopascals, which is equal to 1 atmosphere, or 1 standard atmosphere. Okay, so these are important numbers that you're going to want to know or at least be able to find. So if you look at your Nelson periodic table, how you can find those numbers is you can go to the second page and go to the bottom right hand corner there where it says defined exact quantities. Okay, and it'll tell you, well, let's see, right here, 1 atmosphere is equal to 101.325. It does say use 101, however, we're not going to use 101 kilopascals. The reason being is you always want to use the number that has more digits in it so that your numbers, when you're calculating them, are more accurate. Okay, so you have 1 atmosphere is equal to 101.325 kilopascals, which is equal to 760 millimeters of mercury, which is also equal to 1 bar. Now, you'll notice that there isn't torr in here. Torr isn't a very commonly used measurement for pressure, at least in this course. Okay, so if you're wondering where to find these conversions, you have it given to you on your Nelson periodic table. All right, now how do we convert between units of pressure? So I like to use unit analysis in order to convert. So just a quick reminder here, unit analysis is all about making sure you have the exact same units in the numerator as well as the denominator. Okay, so the reason why you want to make sure you have the same units in the numerator and denominator is so that they cancel out and you'll eventually end up with the units that you want. So let's look at this first one here. We're converting 32.00 kilopascals to atmosphere here. So let's start off first by writing out our given number. So 32, and I'm going to make sure to write the units. Now, for unit analysis, I always need to write this times by and then this fraction sign. Now, we know we want to get rid of kilopascals and end up with atmosphere. So since kilopascals is in the top, I'm going to put kilopascals in the denominator. And then I'm going to put atmosphere in the top. Okay. Now, what that's doing here is our kilopascals will cancel out and we will be left with atmospheres. Okay, and now at this point, all we need to do is fill in the numbers here. So 101.325, so I'm getting that from the conversion line here, okay, is equal to 1 atmosphere. So I'm going to put 1. Okay, so now what I need to do here is I need to take 32 times 1 divided by 101.325. That's what I'd be putting into my calculator. And once I do that, what I'm going to get is 0.3158 atmospheres here. Now, what I've already gone ahead and done here is I've already put it into the proper amount of sig digs, because this number that we were given here has 4 sig digs. So the 3 counts as a sig dig, the 2 counts as a sig dig, and then the last 2 zeros, because they're trailing zeros, those also count as sig digs. So that's why my final answer is going to have 4 sig digs as well. The leading 0 does not count as a significant digit. And then I got to make sure to put my units there. And then I'm just going to put a box around that final answer. Okay. Now for this last box here, we need to convert to millimeters of mercury. So what I'm going to do here is, once again, I'm just going to start off with 32 kilopascals. Okay, times by fraction sign. Okay, I know I want to cancel out kilopascals. It's on the top, so I'm going to put it on the bottom. And I'm going to write millimeters of mercury right there. Okay, now 101.325 kilopascals is equal to 760 millimeters of mercury. Okay, so when I put this into my calculator, what I'm doing is I'm going 32 times by 760 divided by 101.325. And what I get when I calculate that is 240.0197 ... Number keeps on going on forever. Okay, now kilopascals, those cancel out, and we are left with millimeters of mercury. But because this is a calculation, we're always going to want to do significant digits. So once again, we have 4 significant digits in our original number. So I'm going to start by counting from the left here with the first sig dig. So starting at the 2. So 1, 2, 3, 4. So there's my cutoff line. Since the number after the cutoff line there is less than 5, that means that the number in front of the cutoff line just stays the same. So my final answer is 240.0 millimeters of mercury. Okay. For this next row here, we're starting off with millimeters of mercury, and we're asked to convert it to atmospheres as well as kilopascals. So we're going to do the exact same process here. Start with our given number, and then go times by a fraction sign. Okay, millimeters of mercury is in the top, so I'm going to put it in the bottom so that units cancel out. And then for this one, I'm going to put atmospheres in the top. Okay, so 760 millimeters of mercury is equal to 1 atmosphere. So what I'm doing in my calculator is I'm taking 925 times by 1 divided by 760. And what I get is 1.217105 ... Number keeps on going on forever. Okay, millimeters of mercury cancel out, so my units are atmosphere. All right, so with the number that we were given, that's going to have 5 significant digits. So I'm going to want to make sure that my final answer has 5 significant digits. So starting from the left, 1, 2, 3, 4, 5. So there's my cutoff line. So my final answer is going to be 1.2171 atmospheres. Moving on to converting from millimeters of mercury to kilopascals. So 101.325 divided by 760. So what I'm doing is 925 times by 101.325 divided by 760. And I get 123.32319. Number keeps on going on forever. Millimeters of mercury canceled out. We're left with kilopascals. Now we need our final answer in 5 sig digs. So starting from the left, 1, 2, 3, 4, 5. There's my cutoff line. So then my final answer is going to be 123.32 kilopascals. Now, if you were wondering why aren't we using 760 for significant digits, the reason being is because 760 is a constant, and you never use constants for your significant digits. So that's why I didn't put my answer in 3 sig digs, because you cannot use constants for significant digits. An easy way to tell if something's a constant is if it comes from a data sheet, it's probably going to be a constant. All right. So you may have noticed some abbreviations when I showed you the Nelson periodic table before, but we'll go over these again. Okay, so there's some abbreviations that you need to know because they're secretly telling you temperature and pressure conditions. So the first one is STP, which stands for standard temperature and pressure. Okay, so those conditions for temperature, it's going to be 0 degrees Celsius, and for pressure, which I'm just abbreviating to press, pressure is going to be at 101.325 kilopascals. Okay, now where can you find these values? If we go to our Nelson periodic table and we're on the second page in the bottom right hand corner again, you can find that right there. Now it does say use 0 degrees Celsius and 101 kilopascals. Do not use that. The reason being is because you always want to use the number that has more digits in it so your answer is more accurate. So just use 0 degrees and 101.325 kilopascals. Now looking down below here, you can also find SATP, which stands for Standard Ambient Temperature and Pressure. So SATP is like the more realistic, like room temperature settings you probably have. and those settings, or conditions I should say, are at 25 degrees Celsius and 100 kilopascals. So let's go ahead and write that in our notes here. So 25 degrees Celsius, and our pressure is at 100 kilopascals. Okay, so the reason why you need to know these abbreviations and why they are representing temperature and pressure is because sometimes you will get questions where they say, oh, you have this gas at STP or SATP, and you need to be able to know, oh, okay, they're telling me what my temperature and pressure conditions are, and then you just need to look up on your periodic table, or on the Nelson periodic table on the second page. You just need to look up these conditions. You do not have to memorize them. You just need to know where to find them. Okay. So looking at our first law here, which is where we're going to start getting into calculations, it's called Boyle's law. Now, basically, the scientist with the last name of Boyle, he studied the relationship between the volume of gas and the pressure exerted on it. And what he found is that volume is inversely proportional to pressure, as long as you assume a constant temperature as well as a constant amount of that gas. Okay. Now, what does it mean to be inversely proportional? It basically means when one variable goes up, so either volume or pressure, the other one is going to go down. Okay, so to write that out in some shorthand here, if we increase pressure, because of the inversely proportional relationship that Boyle discovered, that means that volume is going to decrease. Okay, so like one way that you can logic it out here is if you look at these pictures just off to the right here. Okay, so as we go this way, we are decreasing volume. Okay, and as you can see in these pressure measurements here, as the volume decreases, the pressure increases. Okay, because there's more collisions between the gas molecules and the sides of the container because it's a smaller container as we decrease the volume. Okay, now as we decrease pressure, that means volume of the gas is going to increase. So that'd just be like, you can see that if you just read the same diagram from left to right here. So as we go from left to right, the volume of the container is increasing and the pressure is decreasing there because there's less collisions between the gas molecules and the sides of the container because the container has increased in volume. Okay. So, as I've said previously, Boyle's law, the assumptions made are that the amount or the moles of the gas are going to stay the same, and temperature is also going to stay the same. So, amount, moles of gas, and temperature of said gas stay the same. Okay, so if we assume that the moles of the gas and the temperature of the gas stays the same, then Boyle's law will hold true. Now, Boyle's law is P1V1 is equal to P2V2. So let's make sure to highlight this. Okay, now P1 and V1, you could think of that as the initial conditions to whatever gas sample you are talking about. whereas P2, V2, you could think of those as the final conditions of the gas sample you're talking about. Okay, so P1 V1 is equal to P2 V2. That's just the formula for Boyle's law that represents this inversely proportional relationship between pressure and volume. So for some examples of calculations using Boyle's law, for the first one here, we have a sample of carbon dioxide gas that occupies a volume of 3.50 liters at 125 kilopascals of pressure. What pressure, so that's important, that's what we're looking for, would the gas exert if the volume was decreased to 2 liters? Okay, so let's write out our list of givens here. Okay, so P1, V1, P2, V2. So reading this question again, so occupies a volume of 3.50 liters at 125 kilopascals. So this at kind of correlates these two numbers. They both belong to the same set of conditions. And since this set of conditions comes first, I'm going to say, okay, 3.5 liters and 125 kilopascals, those are our initial conditions. Okay, now since the question asks what pressure, that means our final pressure, we have no clue what it is. Okay, but our final volume says it was decreased to 2 liters. Okay, so let's start out by writing our formula and then plugging in our numbers. Okay. Or alternatively, what you could do is instead of just plugging in your numbers right away, you could rearrange the formula to isolate for the variable that you want and then plug in your numbers. So I'll just give you kind of like a sample of what that would look like. So since we want to figure out what P2 is, because that's our variable with the question mark on it, because we don't know it, this means we want to isolate this. Now, what we'd have to do is we'd have to say, okay, mathematically, what's happening between P2 and V2? Well, that's multiplication. What's the opposite of multiplication? Well, that's dividing. And we need to divide by V2. And what you do to one side, you got to do to the other side. Okay, we do not divide by P2 because that does not accomplish the goal of isolating P2. So P1, V1 divided by V2 is equal to P2. Okay, so that's what we're going to be using. So P1, that was 125 kilopascals. I'm going to write out the units to show you how they cancel out. Okay, V1, that is the 3.50 liters. And then V2 is going to be that 2 liters. Okay, so if we look at just the units, we're not going to worry about the numbers for a second here. Okay, notice how we have liters on the top and the bottom, so they cancel out. So we know that for whatever value we get for our P2, the units are going to be kilopascals. Okay, so if I take 125 times it by 3.50 divided by 2, what we're going to get here is 218.75. And let's just write kilopascals. Now let's worry about sig digs. So looking at our numbers given to us, the 3.50 that has 3 sig digs to it, 125 also has 3 sig digs, and 2.00 liters also has 3 sig digs. So You always go with the number that has the least amount of sig digs in it, but since they all have 3 sig digs, that just means that our final answer should be to 3 sig digs. So 1, 2, 3, there's our cutoff line. So 219 kilopascals. So I rounded the 8 up to a 9 because the number after the cutoff line was 5 or higher, so that's why we rounded up. Put a box around my final answer, and away we go. Okay, for the next one here, we have a bottle that contains 2 liters of oxygen gas at a pressure of 2.50 atmospheres. What would the volume be? So volume we don't know. If, that should be if, not is. The pressure was decreased to 1.0526 atmospheres. Okay, so let's write out our list of givens. Okay, so because this volume comes first, I'm just going to say it's our initial volume. So 2 liters. Okay, and since it has the word at rated after the volume, I'm going to say, okay, this volume and this pressure is connected. So that should be our P1. Okay, and since it's asking what would the volume be, so V2, we have no clue, but pressure was decreased to 1.0526 atmospheres. Okay, so let's write out our formula. Okay, and again, I'm just going to rearrange the equation first. If you wanted to plug the numbers first, plug in the numbers first and then isolate for your variable afterwards, you can do that too. But I'm just going to show you how to isolate for your variable because I find that that's a skill that a lot of students need practice on. Okay, so we want to isolate V2 because that's our unknown. So what's happening between P2 and V2? Well, that's multiplication. So we got to do the opposite, which is dividing. So then our formula is going to be P1 V1 divided by P2 is equal to V2. And now I'm just going to plug in my numbers. Okay, so 2.50, and I'm going to include units times by 2 liters divided by 1.0526 atmospheres. Okay, so I'm including units so that you can see you don't always have to be using kilopascals for your units for pressure. However, the important part for Boyle's law is that both of your pressure values are in the same units and both of your volume units are the same. Okay, that's what really matters. So with atmospheres, since I have atmospheres on the top and the bottom, okay, P1 and P2 had the same units, so we're all good on that. And now we know, okay, V2 is going to be in liters. And also, because the question didn't specify that it wanted V2 in a certain unit, so it didn't want it in milliliters specifically, that means liters is fair game to write your answer for V2. Okay, so if I take 2.50 times by 2 divided by 1.0526, what I'm going to get here is 4.7501 ... Number keeps on going on forever. Okay. Now, if we look at our given numbers here, so 2 liters, that has 3 sig digs in it. 2.50 atmosphere, that also has 3 sig digs. And then the P2, that one had 2, 4, 5 sig digs in it. So we always go with the least amount of sig digs. So we're going with 3 sig digs. So that means our answer has to be in 3 sig digs. So 1, 2, 3. There's our cutoff line. V2 is equal to 4.75 liters. Oh. All right. And just for your information here, if you have this equation sheet, then you can find Boyle's law right near the top, right here.